In this video, we will be talking about using and interpreting NMR spectra. So we're using NMR spectroscopy. NMR spectroscopy is a very powerful tool in an organic chemist's toolbox. It can be used to identify functional groups. It can be used to identify structures of molecules. It can be used to identify purity of samples. It's very, very powerful for a lot of different reasons, and often at the end of a reaction, we'll take an NMR of a product to really decide whether we have pure product, what we made, and if there's any side reactions that happen that we didn't want. So the principle behind NMR spectroscopy is that we are taking a molecule that has atoms that have spin, so electrons have spin, and we're putting them in a electromagnet that is going to flip the spin, and then we measure how long it takes for it to go back to its original state. NMR really depends on the absorption energy that it takes to take an atom from its lowest energy spin state to its highest energy spin state. And two of the most studied types of NMR spectroscopy are going to be proton NMR and carbon NMR. So proton NMR tells us about the hydrogens in the molecule. Carbon NMR is going to tell us about the carbons in the molecule. So what we see is that electrons, remember from general chemistry, have two different spin states of +1/2 and -1/2. So what we see is that they are totally random in a molecule. They kind of act like bar magnets where the magnetic field is pointing in a particular direction. But when we point a magnetic field in a direction, we apply an external magnetic field, we get all of the magnetic spins lining up in a sample or in a molecule. And then if we take that magnetic field off, we will see these spin states of the individual atoms start to relax to what their original state was. So the principle behind NMR spectroscopy is depending on what is near or around a particular atom, whether it be a hydrogen or a carbon or anything else that's NMR active, depending what's in the chemical environment around the particular hydrogen or carbon, the time in which it takes to relax back to its natural state will change. So what we see is that, and this is described here, this is all in your lab briefings folder if you want to read along with this. So what we see is if we just put a proton in a magnetic field, it would feel the total extent of the magnetic field. But as soon as we start attaching other atoms to that proton, it's going to affect the magnetic environment of that proton. So it responds to both the external field and the fields around it. We call this effect of the atoms around the proton, we call this effect shielding. And we say that the more effect there is on the proton, the more shielded that proton is. So all protons in the molecule are shielded, but some will be more shielded than others, and we measure that shielding by what is called chemical shift. This is an example of an NMR spectrum, and we'll look at many more NMR spectra, both in this and in the homeworks. This is an NMR spectra of chloroform, so CHCl3. And what we see is we have a downfield shift of the shielding on this proton, this CH bond, this proton on CHCl3, such that it's shifted all the way from 0, which is our reference with no protons, to 7. It looks like about 7.3. We call the region near 0, we call this upfield, and there's more shielding on the protons. And as we have less and less shielding, we decrease the shielding. We call this a downfield shift. So we would say that this proton, this CHCl3 proton, has been shifted downfield, and it has decreased shielding from TMS, which is our internal reference. We always compare protons to TMS, trimethylsilane, or tetramethylsilane, and that's a sign of chemical shift of 0. So we would see that this proton has a downfield shift and is decreased in shielding. Usually spectra are run in deutero solvents to avoid having extra signals in your spectra. So as you can imagine, the more de-shielded these protons are, the higher the shift is going to be. The more upfield the more downfield we're going to shift. So the more de-shielded you are, the more downfield you shift. And what we see is that de-shielding tracks with electronegativity. So as we attach more electronegative substituents near a proton, we are going to downshift the proton. So as we go from tetramethylsilane at 0 to ethane at 0.9 to trimethylamine at 2.2 to dimethyl ether at 3.2 to fluoroform at 4.3. So as we see, we go from if we're looking at the terminal proton, it's attached to a carbon versus it's near a nitrogen versus near an oxygen versus near a fluorine. As we get more and more electronegative, we're going to shift downfield. We're going to decrease the shielding. So we say these are de-shielded and they're downfield. And we see as we add more electronegative elements, so if we had CH2F2, we would probably be at 4.8. If we had CHF3, we would probably be at 5.5. So we can increase the de-shielding by having more electronegative substituents near a proton. And as we move further spatially from those electronegative substituents, we are again shielded and we move upfield. So as we're near a nitro group, the protons right next to the nitro group are at 4.3. They're pretty downfield. As we're beta to the nitrogen, we're at 2, and as we're gamma to the nitrogen, we're down at 1. So this is a spatial effect as well. So as we're near electronegative substituents, it'll affect the shift. We'll come back to carbons. Alkenes are also electronegative. sp2 is more electronegative than sp3 hybridized carbons. So sp2 hybrids will have a de-shielding effect on protons, and carbonyls will also de-shield protons as we're near an electronegative O, and this carbon has a partial positive charge on it. So how do we interpret NMR spectra? So there's a couple different things that we see in NMR spectra. We're going to see one, the chemical shift, which will tell us what kind of protons are in the compound. We can see the number of signals to determine how many different kinds of protons there are. We can use the intensity or the peak integration to determine relative ratios of different kinds of protons. And we can use the multiplicity, or what's called the splitting, of each signal to determine how many protons are vicinal, or next to, the ones giving the signal. So if we're examining this molecule here, methoxyacetonitrile, so we have a CH2 and a CH3, what we see is that the CH2 is going to be downshifted because it's closer, it's between an N and an O. So we see a shift at about 4.1. And we see an integration that's given this 2H. This integration of 2H tells us that at this position, there's 2 protons that have this type of chemical environment. And as we see here, this would represent a CH2 group. Our terminal CH3 is near an oxygen, so it is going to be downshifted from what would be expected to be around 1.5. So it's downshifted to about 3.3. And our integration tells us that there's 3 hydrogens, 3 protons experiencing this same chemical environment. So our integration of 3H indicates a CH3. Now, both of these are what we call singlets. It's one peak in the spectrum. But what we see is that if there are protons vicinal, so if there was an extra carbon right here with protons on it, we would see what's called multiplicity and splitting, or spin-spin splitting. So what we see, and I'll scroll down here, I'll have these both up, is if we look at CH3, CHCl2, looking at this CH3, we have, on the carbon next to it, we have 1 proton. If we go up to here, we see that if we're vicinal to 1 proton, or we're coupled to 1 proton, we will experience a doublet. And the intensity of the lines would be a 1-to-1 ratio. If we're looking at this CH3 peak, we should have an integration of 3. We should have a 3H because there's 3 protons at this position. and it should have a splitting of a doublet because we're next to one proton. And then what we see here is we have a doublet, and it's a CH3 integration. It's also upfield relative to the CH group because we're further away from the CLs. If we look at this H, we see that we should have a 1H integration because there's only one H with this position, with this type of chemical environment. And we're next to 3 H's, which if we look up, 3 H's should give us a quartet. And what that looks like is something like this. We have a 1 to 3 to 3 to 1 ratio. As you may have noticed, there's a rule for determining how many peaks will be split, and this is called the N+1 rule. So what this says is that we look at whatever protons we're examining. We count how many protons are vicinal or one away on the carbon next to it, and we do an N+1. So we add 1 to that number to tell us how many peaks it's going to be split into. So using this here, we see that this CH3 is next to 1H. The N+1 rule tells us 1 plus 1 is 2, so we should see a doublet. If we look at this H here, we see we're next to 3 H's. 3 plus 1 is 4, so we should see a quartet. And that can be used for any number of protons. Let's look at another example. So let's try and expect what we should see. So we have a CH3, CH2, Br. We should expect the CH2 to be to be less shielded, de-shielded and downfield from the CH3 because it's closer to the electronegative element, and we can confirm CH2, CH3. And for the splitting, we should see that this CH3 should have an integration of 3, and it's next to 2. 2 plus 1 means that this CH3 should be a triplet. And if we look, we see that the CH3 is a triplet. Looking at the CH2, it should be downfield. It's near the Br. So it should be downshifted. It should have an integration of 2 because there's 2 hydrogens there. It's a CH2. It's next to 3 hydrogens, so we should have 3 plus 1 is 4, so we should have a quartet at this downshifted CH2, which is what we see here. Complicated splitting can come up if we look at an isopropyl group. If we look at this H here, so we look at this CH3. This CH3 is connected to 1H, so we should see a doublet for that. Now note, these CH3s are chemically equivalent. There's no way we could distinguish between these CH3s, so what we should see is a doublet that has an integration of 3 plus 3 is 6. So this is a CH3, but it should have an integration of 6. Since it's next to 1, it should be a doublet. Now this hydrogen should be a 1H integration because there's only one proton with that chemical shift. However, it's next to 3 plus 3. It's next to 6 hydrogens, vicinal to 6 hydrogens. So we should have a 6 plus 1, which is a septet, 7 distinct signals on this peak. So we have 1, 2, 3, 4, 5, 6, 7. And sometimes this gets hard to see when they go into the baseline. So this doublet septet is indicative of an isopropyl group. And I'll let you read over these. Just as an example, looking at this 2,3,4-trichloroanisole, this H is split by nothing, so it's a singlet. This H is split by its neighbor, so it's a doublet. This H is split by its neighbor, so it's a doublet. This H is closer to a chlorine, so it's going to be more downfield than this H. And this H is only next to an oxygen, so it's going to be the most upfield. Now, we don't only have to examine the hydrogens, the protons in the molecule, we can also examine the carbons in the molecule. And the rules for carbon follow the same, except there's no splitting in carbon NMR. So the shift is based off of electronegativity, how close it is to an electronegative atom. And the number of peaks in the carbon NMR spectra can tell you how many different kinds of carbons there are in that particular molecule. So if we look, we have chloropentane. We have 1, 2, 3, 4, 5 different carbons. So we have 1, 2, 3, 4, 5 different peaks. And we could expect that the one closest to the chloride is going to be the most downfield, and then as we move further and further away, they get shifted towards 0. You'll notice the range for carbon NMR goes much higher. It goes up to about 300. It just is a larger range for the chemical shift for the ppm. It's the same for shifting downfield. The more deshielded you get, the more downfield you shift. And you can look up tables for common chemical shifts of representative carbons or representative protons. Note sp2 hybridized carbons are more deshielded, so you'll see them further out. You see next to a carbonyl is all the way down to 200. Your alkyl group is down here. Your aromatic carbons are down here, and that up at 200 you have your carbonyl carbon. We can use all of these. We can use both proton NMR and carbon NMR to distinguish between different types of molecules and different types of products. So let's look at a couple examples of proton and carbon NMR. So I have here the proton and the carbon NMRs of this molecule here, which is known as methyl methacrylate. So let's examine the proton NMR first and then examine the carbon NMR. So I'm going to draw in all of my protons. I have two here, I have a CH3 here, and a CH3 here. Now, as we're looking at this, we can kind of guess how many different proton environments we're going to see. So we have one here. All three of these are the same. We have one here. And you'll notice that these two, while they're both a CH2 group, they are going to be different because one is cis to this carbonyl and the other one is trans to this carbonyl. So we will have two distinct carbonyl CH2 protons. If we're looking at integration, then this doesn't show the integration. We'll have a 3H, we'll have a 3H, we'll have a 1H, we'll have a 1H. Now let me number these. So I'm going to number these 1, 2, 3, and 4. So let's kind of try and determine what is what on this spectrum. So as we're looking at this, we have protons that are alpha to a carbonyl group. We have protons that are alpha to an sp2 hybridized carbon, and we have two protons that are directly on an sp2 hybridized carbon. So what we would expect is probably this proton here, number 2, is going to be the most shielded. It's attached to an sp2, but that's about it. So this is going to be the most shielded. So I would call this one number 2. The splitting I would expect here, there's nothing next to it, so it should be a singlet. And as we can see, this is indeed a singlet. So this is going to be a 3H singlet. The next I would expect is going to be this CH3 that's right next to a carbonyl group. So I would call this number 1. There's no hydrogens next to it, so this is also going to be a singlet. So this is a 3H singlet we see. So this is a singlet. This is a singlet. So we have two 3H singlets, and then we look at these protons, and while it may be difficult to distinguish, I would say the one that's cis to the carbonyl is going to be a higher shift, is going to be more downshifted than the one that is trans to the carbonyl. So I would call this one probably 3, this one probably 4. Now they are on the same carbon, so since these are different, protons that are different will split each other. So this is next to 1. So these should be 2 doublets. So we should see something that looks like this. And as we see, we do have 2 doublets in here. It's kind of hard to tell, but we have 2 doublets, 3 and 4. So this is what our proton NMR would look like. Now let's look at the carbon NMR. So as I'm looking at these, we have to determine what is going to be the order. How many signals will we see? Well, we have 5. But how do we order these? So I'll order them 1, 2, 3, 4, 5. So we have 5 different carbons. Now, as we're expecting, the shielding is going to look the same. So 4 will probably be the most shielded. So I would call this number 4. Followed by 1, which is right next to a carbonyl. So this would probably be 1. And then we have 3 sp2 hybridized carbons. As we saw, the carbonyl carbon is probably going to be the most deshielded, so I would call this number 2. And then between 3 and 5, I would say the one that's right next to the carbonyl is going to be more deshielded than 5. So I would call this 3 and this 5. And we can use these same rules to predict what an NMR spectrum might look like, more so a proton than a carbon. But we can use a structure to determine how many carbon signals we may see, and how many proton signals, the integration of the proton signals, and the multiplicity of the proton signals.